Okay, here was such a great probability question that I got asked this week that I couldn't help but want to share it with you. I thought it was a very good question. We've done quite a lot of videos on heads and tail tossing and throwing two dice and what's the probability of getting all sixes or all ones or the number 10. But here we've got a question that seems very big from the outside. You toss a 10-sided dice 4 times. What's the probability of you getting a 9 or a 10 in any of your tosses? Well, if we were to do this traditionally, we would have to draw 10 different possibilities for every single dice, and it would really fill up our paper. But what we're really interested in is we're interested in actually 2 options. We're interested in not getting a 9 or a 10. We can call this one here anywhere that's 1 to 8, or the probability of us getting a 9 or a 10. So we actually just do 2 branches of our probability tree here. Now, what would be the chance of us getting a 1, a 2, 3, or 4, or 5, or a 6, or 7, or an 8? Well, that probability would be 8 tenths. What would the probability of us getting a 9 or a 10 be? Well, that's 2 probabilities out of 10, so we'd get 10 tenths. And then we actually just continue this for our next toss. In our second toss, we could either get the 1 to 8 option that we had up there, or we could get the 9 or 10 option. And here as well, second toss, we could get the 1 to 8 option that we had here, or we could get a 9 or a 10. And then we carry on, because this was our second toss. Now we would have our third toss, where we would carry on with our option of either 1 to 8 or 9 and 10. Here in this row, we could either get 1 to 8 or we could get 9 to 10. Here we could either get 1 to 8, and here we could also get 9 to 10. And it's getting very tight here, but we can still see that we have first 1 branch, then 4 branches, then 8 branches. Then when we toss the final time, we are going to get 16 branches, because each of these 8 branches is going to give us 2 more branches coming down. And I'm actually not going to fill all of those in, and I'm going to explain why in a little while. Just because I really don't have enough space on my paper, and they're not the important ones. Okay, so when I go down any line where I have a 1 or an 8 underneath, I know that this individual probability is going to be 8 tenths. But because I've gone down this branch, first I've got a 1 to 8, then I've got another 1 to 8. The overall probability here is going to be the 8 tenths for this second one, which is the individual probability. And I've also got this probability here. So I'm going to have 8 tenths here. And before I go any further, I'm probably going to say, well, this is the chance of me getting 1 to 8 is 8 tenths, but should I keep it as such a large fraction? Well, I could actually quite easily convert that to 4/5. So maybe we should do that for all our probabilities where we have a 1/8. Why don't we instead say, well, that's the same as the fraction 4/5, because then we actually have smaller numbers to work with. And then if I carry on and I throw my dice a third time, I would have, to be able to come down this row here, I would have had my probability of throwing a 1 to 8 first time, and the probability the second time, and the probability the third time. So to get to this point here, I'd have first thrown any number 1 to 8, then any other number 1 to 8, and then any other. So I would multiply these probabilities together. By the time I come down to my very, very last position here, this last 1 to 8, I will have followed the same routine 4 times. So I will multiply all of those probabilities together. So the probability of me coming down this route and always only getting a 1 to an 8 and never a 9, so the probability of me always getting a 1, a 2, a 3, a 4, a 5, a 6, 7, or an 8. There's no 9 and no 10 in anywhere going down this right row, tree. It would be 4/5 times 4/5 times 4/5 times 4/5. Okay, which is the same as 4/5 to the power of 4. We can write that in maths terms as well. Okay, what would we do here then? Well, 5 times 5 is 25. So we get 25 times 25. Up at the top here, we've got 4 times 4 is 16 times 16. And 25. And we have 16 times 16, which is 256. So the probability of us getting a 1 to an 8 is 256 divided by 625, which gives us a probability of 0.41. And that is to 2 decimals. The actual probability is 0.4096. Okay, so now we know that the probability of always going down this route, and this is where we only have a 1 to an 8, is 0.41. Everywhere else in our tree, we've got a 9 or a 10 somewhere. So here we had a 9 or a 10. Here we had a 9 or a 10. Here we had a 9 or a 10, and then we went down to 1 or 8, but there was a 9 or a 10 up here. Here we had a 9 and a 10, but then we went down to 1 to 8 here. Here we had a 1 to 8, but we went down to 9 or 10. So here's a 9 to 10, here's a 9 to 10, here's a 9 or 10, and in this last one, so there is a 9 or a 10 everywhere else except here. Here we went 1 to 8, but here in this last one here we had 9 to 10. So we've got all of these other 15 possibilities where there is at least 1 9 or 1 10. We could calculate those and add them all together, all of these and possibilities, and then add all of the or possibilities, or if we worked out this one, we could add all the other 14 possibilities as well. But it's actually much, much easier to just say that the probability of getting a 9 or a 10 is actually 1 minus the probability of getting a 1 to an 8. And we already know the probability. That was quite easy to work out because we only had to go down one branch of the tree. So the probability of getting a 9 or a 10 is 1 minus 0.41, which is 0.59. Let's do a little check. 0.59 plus 0.41 is going to give us 1. So now we know the probability of that, and you are done and ready. So the probability when you toss a dice 4 times of getting a 9 or a 10 is actually 0.6. Good luck.